On the night of March 8, 2014, Malaysia Airlines Flight 370 took off from Kuala Lumpur headed for Beijing. For the first 40 minutes, everything was completely normal. The plane reached its cruising altitude of 35,000 feet, and as it approached Vietnamese airspace, the cockpit delivered a routine sign-off. "Good night, Malaysian 370. Seconds after that transmission, the plane's transponders were manually turned off. Instead of continuing north, the aircraft made a sharp left turn. It flew back across the Malay Peninsula, went dark to air traffic controllers, and spent the next 6 hours heading thousands of miles south over the Indian Ocean. Between 2014 and 2018, investigators spent over $150 million scouring the southern Indian Ocean. Teams combed thousands of square miles of water in the most expensive search in aviation history. They found absolutely no wreckage. An investigative failure of this scale created an agonizing open wound for the families of the 239 people on board. Without a crash site or a final report, the absence of answers created a vacuum quickly filled by wild, conflicting theories about what happened that night. In late December 2025, the marine robotics company Ocean Infinity officially restarted the hunt. Their main exploration ship, the Armada 8605, arrived in the Indian Ocean with a strategy aimed at a highly specific patch of the seafloor. The Malaysian government agreed to restrict no find, no fee contract. If Ocean Infinity locates the wreckage, they receive $70 million. If they don't, the company absorbs the entire cost of the operation. That financial risk demonstrates their absolute confidence in a new set of data. This mission is designed specifically to solve the physical and digital blind spots that stalled earlier searches. Researchers have identified exactly where the early missions went wrong, moving past the broad, wide-net sweeps of the past. The early searches relied on the assumption that MH370 flew on autopilot in a straight line until it ran out of fuel. That assumption generated a massive, unmanageably large search corridor stretching across the ocean. To refine that path, investigators are now looking at WSPR, or the Weak Signal Propagation Reporter. This is a worldwide network of low-power radio signals maintained by amateur radio operators. These invisible waves crisscross the globe continuously. When a massive metallic object, like a Boeing 777, passes through a signal, it acts like a tripwire. The plane causes a tiny, measurable disturbance in the radio waves. Aviation experts debate whether WSPR data is clean enough to track a plane on its own, since weather or other aircraft can cause similar interference. But supporters point out that by connecting hundreds of these disturbance points from the night of the disappearance, a distinct curving route emerges. This digital trail matches satellite records to suggest a manually flown path that deviated significantly from standard air routes. This volume of data allows investigators to shift their focus away from a drifting autopilot scenario toward a highly specific pocket along the 7th arc. Pinpointing a crash site years after the event is difficult in an ocean that is constantly moving, driven by winds and seasonal tides that shift throughout the year. Researchers worked with fewer than 30 confirmed pieces of aircraft debris that eventually washed ashore on distant beaches. These fragments carried a natural diary in the form of attached barnacles. By analyzing the growth layers of their shells, scientists determined the exact water temperatures the parts moved through over time. This map tracks those findings. By feeding the temperature data and the Indian Ocean's seasonal currents into supercomputers, scientists could trace the drift paths backward. Running these models in reverse pulled the scattered debris from the African coast back to a single origin point on the 7th arc. The condition of the metal also revealed the impact force. The severe tearing on a wing part called a flaperon indicates the aircraft was not configured for a slow, smooth landing. It struck the water in a high-speed dive, which suggests the plane shattered rather than skipped across the surface. A high-speed impact prevents the aircraft from breaking apart over a wide area, meaning the wreckage is tightly clustered on the seafloor. Spotting a target that small in the deep ocean requires extreme technological precision. The search area sits within the Roaring Forties, a latitude famous for continuous winds and waves that can reach the height of a 4-story building. Below the surface, the terrain drops off into a landscape of jagged underwater volcanoes and trenches nearly 23,000 feet deep. During the first search window, ships dragged sonar cables miles behind them. In this cross-section, the sonar waves hit the mountain peaks and bounce back, leaving massive, dark shadows directly behind the ridges. Anything sitting in those trenches remained hidden. Ocean Infinity is bypassing this problem by deploying swarm robotics. Instead of pulling a cable, they launch a fleet of Hugin autonomous underwater vehicles. These untethered drones dive into the water and operate independently in a matching formation. Looking back at our trench model, these autonomous drones navigate the jagged terrain by flying close to the seabed. They slide directly into the shadows that blocked the old sonar arrays, scanning the deepest pockets with their own localized instruments. Onboard AI processes the incoming sonar data instantly. The software analyzes returns in real time, distinguishing between the irregular shapes of natural rock formations and the jagged geometric edges of aircraft aluminum. By combining better route data with advanced robotics, the search teams can finally peer into the darkest terrain on Earth without leaving any physical blind spots. If the drone swarm flags a match, the surface ship will deploy remotely operated vehicles to inspect the site. They will visually document the entire debris field before any decision is made about recovery. The layout of that debris will immediately solve the physical questions of the crash. A mostly intact fuselage points to someone attempting a controlled water landing, while a highly fragmented debris field confirms a steep, high-speed dive. But the true targets of the mission are the flight data recorder and the cockpit voice recorder. Even after 12 years submerged in freezing, high-pressure water, the solid-state memory banks inside those steel cylinders are likely still in good condition. Those drives are the only indisputable sources left. They hold the mechanical data and the audio recordings required to explain exactly who was at the controls and why the plane turned. Finding the aircraft will permanently close the door on a decade of damaging rumors. It will put an end to theories of stolen planes or hidden military bases. For the aviation industry, a final report means engineers and regulators can study exactly what happened. They can implement safety rules to ensure a modern commercial airliner never simply disappears from radar screens again. Most importantly, it gives the families of the passengers certainty. Locating the site gives them a physical place to grieve and allows formal memorials and remembrance protocols to finally move forward. This mission strips away the guesswork, relying entirely on refined math, reverse ocean modeling, and deep-sea robotics. It is the final, best chance we have to transform aviation's longest-running mystery into a closed tragedy.